Okay, our final speaker for today is Mark Batty. A lot of us know Mark already. He's going to be speaking about Symbolic MRD.
Thank you. So this is very much joint work, and Jay Richards, who was the first author on this paper, can't be here. I'm using his slides, which have this strange aspect ratio. I might hand back comments because I don't love it, but bear with me. So this work is about a model that follows on from what Simon Cooksey was talking about. He mentioned MRD, and this is an extension of that work called Symbolic MRD. This is very much in the vein of the sort of PL work that we're used to. We're addressing systems with shared memory concurrency. We're going to be talking about the mutation of memory across threads, data races, that kind of thing. And we're interested in being able to say something about systems components, drivers. Our audience are fairly technical, and there's a small number of people who care about these corner cases of the system. But if we don't get these corner cases right, if we don't define the underlying behavior of the system, then we can't really say too much about security of the thing. So we think there's value in this. The approach that we take is to define mathematically the behavior of the system in a mathematical object called a memory model. And then try to use that to do verification. It turns out even defining the model of the system has been a huge pain because of some details I'll tell you about. Let me start with one of these tests that many people in this room will have seen hundreds of times. So here we've got, I can use the mouse. We've got a little test here. It's got two threads. These things are going to run concurrently from the top to the bottom in the first instance. So this thread will read from some global value x, put it into a local variable R1, and then it'll write to some global Y. And it's going to do that at the same time as the other thread's running. That other thread's going to do the symmetrical thing. It's going to read from Y and write to X. And the question we're trying to answer is, how does this program behave? The way that we have decided in many cases, in many languages and many processor architecture definitions to answer that question is to map the program to what we call an execution. So some dynamic behavior of that program made up of reads and writes, just one unfolding of control flow, one behavior. And this is what that looks like. So we have to decide which executions are allowed and which aren't. A typical way people will think about concurrency is this model called sequential consistency. And there, you can think of all of the lines of the program being interleaved with each other and then run in sequence. The way we model that is to say that there's some total order over the events of this execution, and we'll add some additional constraints, which are any reads. So this RF green arrow is called reads from, and it indicates where a read is getting its value from, the write that a read is getting its value from. Reads from has to be in this total order. And program order, so the order of code within the thread, has to be in program order. And we can only read from the immediately preceding write to the same location. We can't read future writes or stale writes. So the question is what's allowed for such a program or for this execution, given all of the possible ways to construct a total order. So we can, there's an assumption that the initial value of x and y is 0. So here we can read 0 on both sides. That's absolutely fine. And then do the writes. That's okay. We can do one of the writes first. So we simply execute the first thread all the way, do the write, and then read from that write on the other thread. We can do it the other way. But we really shouldn't be able to do this, where we read from sort of like the future on both sides. That makes a cycle, and we no longer have a totally ordered relation here. The trouble is that the computers that we use do exhibit this behavior. They morally relax this total order, this constraint that program order and reads from be in a total order. They do something like this, where they actually may reorder the accesses on one of the threads, suddenly allowing this outcome we didn't expect. If you don't realize this and you're programming some systems component, you'll get a bug. Worse, this happens non-deterministically as you execute, so that bug may manifest itself sometimes, which is not great. So yeah, we would like to define what exactly is allowed in such a system. The thing is, what we've been able to express so far is the definitions of computer processors, but we've struggled with programming languages because they do compiler optimizations. So what I'll go into here is several tests where the compiler optimizer is coming in and using some information that it knows to do some reordering in your program in a way that current models don't express, but the model that we present here does. So yeah, let's go. First, let me describe the thin air problem that Simon alluded to. So this is a problem with the C++ memory model. That very much restricts the behavior of some execution according to some shapes over that execution. It actually doesn't it doesn't enforce program order in the sort of program that we were looking at before at all. And it sort of gets worse because if you hook up dependencies between accesses, so this is a subtly different program where we're loading X into R1, this local, and then we're using the value of that local to decide what value we write to Y. These really ought to be in order. You can't do the write until you know what value to write. The trouble is, so you know, how do we decide what behaviors are allowed from this program? C++ goes and allows you to see pretty much anything. So it allows cycles, it allows cycles of this shape. It doesn't forbid them. And this means that in these executions, you can satisfy the read values without constraint from the writes. So seeing 5 would be acceptable in this program, even though 5 is never written. And so would seeing 7 be allowed. These are all allowed by the concurrency model, but they're forbidden on any combination of compiler and underlying target architecture. And they make reasoning about your code, these thin air cycles, impossible. So we would like to forbid them. They should be forbidden. The current model doesn't do it. So I've kind of shown you two extremes of how we treat these execution graphs with whether they have cycles or not. We can take program order and we can say all of program order is enforced. But then that was too strong. The actual processors that we use and the compilers that we use make behaviors that don't match that specification. And then we can go all the way in the other direction where we have program order totally free. It's not respected at all. But then we can't really reason it about our code and it produces wacky behaviors that are unreasonable and don't happen in practice. So what we propose, well, what we do in this paper is we have something called a dependency relation. And it's a piece of program order that only exists when there's a true dependency between two events. So a read carries a dependency from another to a write if it really has some kind of data or control dependency from the read to the write. And there's all sorts of circumstances under which those can be removed by the compiler. And we're going to try to capture that. So here is one of those circumstances. Now this is interesting. This is two pieces of code. There's code up here, 2 threads, that are optimized to these 2 threads down here. Now, this is really similar to the last program. Again, all these programs are basically very similar. In fact, the thread 2 is the same. But thread 1 has this little expression here, 1 divided by naught of R1. And in C, dividing by 0 is undefined behavior. What that means is if you do a divide by 0 in your program, the language specification says it can do anything. It can catch fire. You can't make any assumption about the behavior. The compiler will take that as a hint that you have not done that because you're a good programmer. So it'll assume that you didn't write 0 there. So in this division here, the compiler will assume that's not 0. So not R1 is not 0. It must be 1. And it'll rewrite that line to be a concrete 1. And then suddenly we're in this circumstance where actually there's no dependency between these 2 lines. And the compiler optimizer or the underlying hardware can reorder these things. And in fact, this behavior where we read in a cycle should be allowed for this program because the optimizer may reorder. Now, this might sound far-fetched, But what we have found is that the compiler is really doing these things. So this here is a website called Godbolt, Compiler Explorer. It just allows you to run compilations of programs. We've got the program I just showed you here, and there's the division in the program. And here's the compilation of that program down to ARMv8. And if you look specifically at this line 3 in the compilation, this here is defining W9, and this W9 is used in a store that corresponds to this store of Y here. So the compiler has figured out that the store must be of a concrete value 1. It's really done the optimization that I just showed you. So if we're going to model the behavior of C++ compiled through Clang down to ARMv8, we need to model this optimization leveraging undefined behavior. And none of the models of the C++ concurrency, including the one in the standard, do this right now. So there's more than one place that the compiler will capture information from that it'll do its analysis with and optimize based on. So disturbingly, one of the places is it'll make some of it up by making choices. So here is an example where the compiler is over-aligning objects in memory. So we know that our objects will be aligned according to 16. And so if we get a pointer to something, so the pointer of P is in R1, and we check its value modulo 16, we know that's going to be true. The compiler will know this alignment. It can strip out this if statement because it's always true. And then there's no dependency in the optimized code between the load and the store. And it would be perfectly acceptable to reorder the right of Y above the load of P. So like this, information entirely outside of the language specification affects the behavior of the program. We're calling this extrinsic choices. So these are things like alignment, constraints the compiler imposes on your code. So here's another thing a compiler can do in order to reorder and provide you with one of these cyclic executions, and that is decide on aliasing. So in this code, here's the initial code at the top, we're making an integer x, and then we're allocating something into P. And when we do that allocation, the compiler knows that it's not going to allocate over x. X is going to be disjoint from this allocation. So when we get down to this left-hand thread, we're doing a load of whatever's in P and then storing to X. If those happen to overlap, we would need to keep them in order. But because we allocated after defining X, we know that they're disjoint and we can reorder them. So in this program, it's acceptable to reorder the memory accesses on the left-hand thread, and you can see that cycle again. So we had a previous model, the one in Simon's thesis, in fact, that tries to solve this problem called modular relaxed dependencies. And, well, let me just point back at where, no, it's here, good. The modular relaxed dependencies does impose this acyclicity condition where dependency union RF rather than program order union RF is guaranteed to be acyclic. It makes its decision using these things called event structures. So these are a bit like the execution graphs, but they depict multiple executions at the same time. So here we've got reads at the top. It's the same read in conflict. So a single execution can only perform either the read of x5 or the read of x0, but not both at the same time. You've got to pick one. And similarly on this side, we have another conflict. So this is representing all the compositions of these two choices. Cool. We can draw dependencies on this graph between the loads and the stores, and in fact we do to begin with. The trick, well, when you execute, what you do is you select one of the choices of the reads and then construct an execution with it. So here, these central read of x5 and read of y5, these are the choices that we're making to execute, and the other parts of the event structure we ignore. The thing is, with this much structure, we can see more than one path of control flow through the program at the same time. So here's a little bit of event structure that corresponds to this program here. And if you look, we're reading from y, we're checking the value that we got from y, and then in either case, we're writing 1 to x. So a compiler will see that and go, well, you're writing 1 to x regardless. I can just remove this conditional, do the load and the store. And in fact, I could even reorder them because there's no real dependency here. In modular relaxed dependency, what we do is we spot this symmetry across the two conflicting reads. We spot that the write is done regardless. And in this case, we do something we call lifting, which is we remove the dependencies. So modular relaxed dependencies sort of captured some of these issues, but it didn't deal with undefined behavior, and it didn't deal with extrinsic choice, and it didn't deal with dynamic memory. But it also enumerated all of the possible values explicitly for the read. And this meant that calculating this model exploded horribly when we tried to build tools. And like Simon said, we really believe in building tools. We take these models to the International Standards Organization, try to discuss them with the people who specify C, because the corner cases in these models inform them about their language. So what we do in Symbolic MRD is we have a more scalable, thinner, free memory model. It deals with undefined behavior. It deals with extrinsic choice. It also deals with global analysis. So like if you do a value range analysis across your whole program, work out X that is always 1, you can incorporate that information with this model. And we have a tool for this. This is going to appear at OOPSLA, this paper. So in Symbolic MRD, rather than having those concrete read values, we have symbolic read values, which means that that complicated event structure crushes down a bit. We still have conflict, but not on reads. Let's see. The thing that we do to intervene on the normal memory model of C++, these execution graphs, is we insist that every write is justified. We have this structure called justification here. So on the right-hand side, we've got a write at some location of some value with some label. And we capture on the left-hand side its control dependencies in this P and its data dependencies in this D. And you'll see that this delta is used to record forwarding choices and elision choices that get made across the whole program. This justification structure will turn into the dependency relation, semantic dependency, when we make the executions. We start by just recording every read to write as a dependency when there syntactically appears to be one. So if there appears to be a data dependency or control dependency, we'll stick it in as a P or a D, and we'll include one of these justification structures to the right. We're going to then take the set of all those justifications and do something we call elaboration. So elaboration is building more justifications. We sort of monotonically increase the set of justifications based on things that look a bit like compiler optimisations. So we do a load forwarding step. Here, in this example, we're loading from X twice. There's no reason to do that. We could reuse the value of the first load in the second. And then we're going to reflect that possibility by adding a justification. And what that justification does is, rather than recognizing a dependency, a control dependency, you see through this conditional here, on R2, as in the original program, we now have this changed to R1 because we've done this forwarding from the first to the second. We have to record that we did the forwarding, and then we can simplify the justification, and we've got rid of a control dependency in the program, just like a compiler would do. It's removed the control dependency in the code. So that wasn't a real dependency, it was something that could be removed. We have another one of these optimizations called value assignment. So here, if you look in the true branch of this program, we know that R1 is 1. That follows from being in the true branch. So this this R1 is not actually, it can't be anything but 1. There's no data dependence for this right of y on anything. There's actually a control dependence that's trumping it. And yet, in the justification that we initially draw, the data dependence is there from R1. So what value assignment does is it recognizes that constraint, and so in particular, it pulls the constraint on the value of R1 out of the control dependency and simplifies the data dependencies based on that. So that's value assignment. Strengthening is the addition of spurious dependencies. So we can add dependencies by saying stuff like this. So we've like inverted and introduced a false dependency. This looks like it's going backwards, but what this allows us to do is reform the conditional structure of trees of conditional statements and match them up with one another. So, if I have a bigger program, I can use this to remove more dependencies. But I do have to like strengthen and then do another step. Lifting is kind of the inverse of this. So let's see. In this program, we have a store to y here of R2. We have a store to y here in the other of R3, and both of those are reading from Z. So the dependency for this store of y in both cases comes as a data dependency directly from Z. We can see this. Let's see. Here, R2 is a data dependency of this right 4. And that right 4 is on this side, you see. And right 6 over here has a data dependency on R3. We know both of those are going to be Z. So in lifting, what we do is and we can see that in both conditional choices, so whether R1 is 1 or R1 is not 1, that covers all the logical space, we can collapse these down and remove the control dependency, maintaining the data dependency, if that makes sense. So this is lifting. So then we have program-wide guarantees. So this is guarantees that you have about the choices of values that are read that are applied across the whole program. So this could be like value range analysis. That alignment information that I mentioned at the beginning could fall in here. This might be where we impose something like a memory model of a memory layout model like Kevin has. Like he was talking about before. And the idea here is we get some assumption from that global analysis, and we can use it to satisfy and simplify the conditionals and the data dependencies. So here we have a justification of this right of y that has a conditional on it, but we know through our program-wide analysis that is going to be satisfied, certainly. So we can add this new justification based on that. Undefined behavior, we can spot these patterns like division by 0 or modulo 0, dereferencing a null pointer, these things, and we can say that the undefined behavior never happens. So the thing in the denominator was never a 0. We can add those as we can simplify the justifications based on that. So here is the example we saw at the beginning. We get to assume that R1 was not 0, and that would allow us to add a new justification here with a concrete value of 1. And this is what allows us to ultimately build an execution with no dependency there and see the reordering. Cool. So there's another class of undefined behavior, which is things like data races. These occur across threads. We can flag executions as undefined in this model. So we can repeat all of these undefined behaviors as well. So this is stuff like race conditions and use after free on initialized values. So we have a tool for this. The whole reason that I'm using J slides is because these are actually handwritten in JavaScript. And it means that I've got the tool running here. This is one of the examples we saw at the beginning. We've got the read of X. It's very small. You can't see it necessarily at the back, but it's got the read of X and the write of Y. There's dependency on the first thread. Similarly, there's a dependency on the second thread. And this says that this test should be forbidden in our test case And in fact, there is no execution here, and the test case's condition is satisfied. So in fact, we have forbidden this test as we should. If I go to the next one, this is the division by 0 is excluded, the undefined behavior inference test. And we see here one of the executions repeated. I can cycle through executions, and I can find the one, if I keep going, I should be able to find the one that has the cycle and reads from. There it is. So that's allowed because there isn't a dependency on the left-hand thread. It's been removed. I just want to set this going and say that one of the problems with these kinds of models is that you're having to do this analysis across all of the paths of control flow in the program to try to understand whether there's a dependency or there isn't. And it just means there's quite a lot of information to kind of internalize and look through in a tool. It turns out that writing such a tool can be very, very slow. And before this paper, these tools would take, sometimes hours to run. But I've just run 267 tests, and I've got, these are taken from the ISO, they're taken from all the previous papers on thinner problem. And I can develop the model very quickly because this tool will run in a matter of seconds. It's a big advance on previous tools. I should say the one failure we have here is actually a disagreement on the outcome that should be allowed. We have this fail 12 is because we don't handle 11 of the tests because they feature stuff that isn't in our language. But yeah, the speed of this tool is a big deal for us. It means that we can do things like Go. When we talk to the ISO, they can say, how about this? And we can just run it live and say, well, we think it behaves like this. What do you think? So that's very nice. We did a bunch of benchmarking over this, which was very good, very quick. And what else to say? Reach my conclusions. So what we have is a model here that we think solves the thin air problem. We got a tool that runs it really quickly. It allows global analysis. It takes into account pointer aliasing. So we've got dynamic memory. It sort of seems to tick a lot of the boxes. The thing I really like about it is that by interfacing with the existing C++ specification through this semantic dependency relation, we can fairly easily explain the behaviors of the compiler in a way that fits with the existing specification. The spec doesn't need huge changes. We just need to say, we're going to define a semantic dependency relation. That definition is pretty complicated, but to begin with, it can be external, and we have tools to generate it for small programs. Scalability is good for the field, but terrible for if you wanted to look at real code bases. So this is something we want to work on. I think I've got a minute or two for questions. Thanks very much.
Thank you, Mark. Indeed, as you say, we have time for maybe 1 or 2 questions. Maybe I could ask you, given that this is VeTSS, what about verification?
We've started using this for verification. So the kind of code that we look at is quite small. We started looking at RCU, which will be familiar to you. Prior work with Brajesh, we verified RCU over the existing C++ memory model. It threw up some interesting things. Reordering within a thread is not something that the previous verifications have taken into account, and it looks like there were bugs allowed to harbor that would be witnessed in the presence of compiler optimization. So we've got something together that we're submitting on that.
So people have been looking into partial order reduction, and I guess this is a kind of generalization of that, where you are relaxing some of the causalities within one thread. Have you thought about generalizing partial order reduction to this setting?
The thing is I think that's more or less what we're doing, but we're doing it very much intentionally according to what we think the compiler is going to do, if that makes sense. So if we did that, I think it's more or less what we're doing. the whole point here is to put an envelope around what the compiler is allowed to do. So these choices are extremely intentional and developed, honestly, over years by handing tests back and forth with compiler engineers. So yeah, that's exactly what we're up to.
Does that answer your question? Yeah. Okay, great.